A pyramid is constructed by gluing together three right triangles with areas A, B, and C, so that their hypotenuses form a triangular base of area D. Prove that a squared plus b squared plus c squared equals d squared. A student showed me this question from a math competition paper, and I was very intrigued by it because it's so similar to the Pythagorean theorem, except that here instead of squaring lengths, we're actually squaring areas. So I couldn't see how any of the standard proofs of the Pythagorean theorem can apply to this problem. In this video, we'll look at 3 proofs, all quite different, and then we'll talk a little bit about this result in general. For method 1, we're going to unfold the pyramid in 2 dimensions. And what we can notice with the adjacent pairs of sides is that they must be equal in order for the pyramid to fold up to the same point. If we called the outer sides x, y, and z in pairs, and the sides of the inner base a, b, and c, we can then use Heron's formula, which allows you to get the area of a triangle in terms of the 3 side lengths. S is half a plus b plus c, so we can rewrite the whole expression for the area in terms of a, b, and c. We're interested in d squared, so we can get rid of the square root. When we expand these 4 brackets, most of the terms cancel and we're left with these 6 terms. Now we can use the Pythagorean theorem to replace a, b, and c with their expressions in terms of x, y, and z. Then with some more clever algebra, or brute force and a lot of patience, you can cancel out most of the terms again and you're left with these 3 terms, which does turn out to be the square of xy on 2 plus the square of yz on 2 plus the square of zx on 2. In other words, the square of the areas of the 3 triangles. Sorry for not showing all the detail of the algebra, but I want to move on to method 2, which is less algebraic because it makes use of vectors. In particular, the cross product of 2 vectors in 3 dimensions. The cross product of a and b, for example, gives a third vector which is perpendicular to both a and b. The magnitude of the cross product is the magnitude of a times the magnitude of b times sine theta, which conveniently means that the area of the triangle spanned by a and b is half the magnitude of the cross product. These properties are all going to be very useful in this problem, because if we label these 3 vectors a, b, and c, they're all perpendicular to each other. Also, the area of the triangle on the base is going to be half the cross product of c minus b, a minus b. D squared is then the square of that. We can expand these brackets to get 4 cross products, but the last one, vector b crossed with itself, is going to just give us 0. Next, we make use of the scalar product or dot product, which is obtained by multiplying the components of the vectors in pairs and adding them. And what's particularly useful here is that if you take the scalar product of a vector with itself, you end up with the length of that vector squared. Our expression for d squared is a length squared, so we can rewrite that as the scalar product of this vector with itself. To expand this scalar product, we would get 9 terms, but most of them are going to be 0, because the scalar product of 2 perpendicular vectors is always 0. If we look at the first term in our expression, a cross c, it's perpendicular to both a and c, which means it's parallel to b, whereas b cross a is perpendicular to b, so the scalar product is going to be 0. All we're going to be left with is these 3 terms, a cross c dot with itself, b cross a dot with itself, c cross b dot with itself, and again we can write these as a length of a vector squared. And that pretty much gets us there because a cross c is length of a times length of c, as they're perpendicular, so these sum of 3 squares then is the sum of squares of the 3 triangles a, b, and c. So still a fair bit of vector algebra there in method 2, but I did at least show all the steps there, unlike method 1. Alright, so on to method 3, and what we're going to do here is reposition our triangles so that the right angles are on the origin of a 3-dimensional axis. Now, no matter exactly where the triangle D is, we can represent it using the equation of a plane in 3D space, ax plus by plus cz is equal to 1. The axis intercepts are at 1 on a, 1 on b, 1 on c, and the origin. Now we use the equation for the volume of a pyramid, 1/3 base area times height. And by taking each triangle in turn to be the base, we can write this volume in 4 different ways. We don't yet know the perpendicular distance from triangle D to the origin, let's just call it h for now. And we can write capital A, B, and C in terms of D, little h, little a, b, and c like this. To find the perpendicular height h, we want to make use of the fact that this plane, ax plus by plus cz is equal to 1, has a normal vector ABC, meaning this vector is perpendicular to the plane. If we start at the origin and travel along this normal vector, wherever we get to must have coordinates Ka, Kb, and Kc. If we sub these coordinates into our plane equation, we can then solve to get k in terms of a, b, and c. Then we can solve for the length h, which is the length of the vector k times n, which will be 1 over the square root of a squared plus b squared plus c squared. Now we can sub that into our expression over here for dh all squared. It will cancel out the little a's, little b's, and little c's. We're just left with d squared on the right and a squared plus b squared plus c squared on the left. So there we are. Method 3 is definitely my preferred method of the three. Less algebra than the other two methods and more intuition as far as why this theorem actually works. It is a well-known theorem called Degua's theorem, and it is a generalization of the Pythagorean theorem. Interestingly, it can be further generalized to apply to any number of dimensions, which is really cool but kind of a bit hard to visualize, so I'll leave this video here. Hope you enjoyed it, give it a thumbs up if you did.